Good morning, everybody. I'm going to describe you a dual frequency tropospheric correction model for a real-time GNSS application, which optimally exploit the GNSS data and total delay from real-time or near real-time source from on the one hand side, and on the numerical weather model for prediction on the other side. So I will start with a motivation and the procedure description, then comparison of these two sources, in fact, because we would like to combine them, and to show some assessment of the case studies which we are introduced to assess the strategy. So the goal is really to have a high accurate and stable augmentation tropospheric correction, meaning zenith hydrostatic, zenith the delay at any place and any time for the real-time application, so even up to the surface. And there were some impact studies already showing that the PPP convergence, it has a positive impact, for example, by Elu et al. In MT 2016, or for example, my colleague showed a GNSS kinematic balloon flight experiment, which was in a GPS solution 2017. So another studies as well, where the tropospheric corrections were used as an external model for strengthening the PPP in a real time. And the main challenging point here is the modeling zenith weather delay, because weather forecast really has a good prediction of the pressure hydrostatic component. So the basic component here is originally that we have a numerical weather model, 3D grid. We do some approximation to create a tropospheric model on a 2D grid in a reference level. Either the numerical orography or numerical model orography or another reference. So we go into the vertical approximation, then into interpolation in time and space, and then again go into the location on the right-hand side of the location of the user. So that's meaning real-time application. It can be even above the surface. And now we would like to ingest there also the GNSS information, because it can be an interesting source of the contribution. So the basic idea is to have a dual layer model, because in fact the background model is based on the numerical weather model forecast, which is distributed in a very good spatial resolution and homogeneously, and it is let's say safe in all the domains and the time, and we can even predict it very reasonably. But then we have also these precise zenith total delays in real time or near real time from the permanent station with a high resolution. And the principal idea is very similar to what is done today nowadays on the assimilation on the zenith weather delays into the numerical weather forecasting, to improve the component in the numerical forecasting in component of the humidity, because the zenith total delay is really sensing the humidity, and this is a highly variable component. But we have advantage, because if we want to combine these two products, we are just focusing on user parameters of interest, and particularly zenith weather delay. And that is our advantage, that we can use a simplified approach really to do this combination. So the first layer model is a background GOP augmentation model, so exactly what we get from the 3D grid of the numerical weather forecast, and correct it into the reference level, and then enable interpolation to the user, and even it can be based on the forecast prediction of the weather model. And then if we have, and we also can use a vertical approximation, because we have a 3D grid in original, so we can make auxiliary parameters for the vertical scaling, which is then done in a precise way. And then optionally, if we have a GNSS reference network, and we can provide the zenith total delays from the real-time or near real-time capability of the production, then we can improve this wet part by the combination of these two, and this is the interest of this study. So the data set on the background is a GNSS for SWAG benchmark campaign. I showed it last year. There is also a paper about this. It's in the domain of the Central Europe, and it's covering really several even study case in 2 months in 2013, where there are floods in Central Europe. And we have two numerical weather models. One is error analysis in long term, error interim, low resolution one, just for testing purpose, because we have a different time scale even to use them. And then we have a real weather forecast from the WRF, operated by Institute of Computer Science of our colleagues in Czech Republic. And this has a regional grid of 9 to 9 kilometers, so in high resolution. And it's a really operational forecast, which has the domain over all Europe, or most of the Europe. And we had a GNSS station in this central part of Europe, over 400 stations. And this is exactly what you can see, the two epoch snapshot for the era interim on the left-hand side and the WRF forecast on the right-hand side. So you see the weather, and you see now only the zenith weather delay component, which can reach up to 30 centimeters, for example, in this domain, and it's highly variable in time and space. So this is really the situation where you see the change front is going through the domain. And now about the procedure, we are first preparing the GNSS data because we have zenith total delay. In fact, we can introduce already our background model, so we can subtract the zenith hydrostatic delay optimally already in a consistent way from the background model, so from the numeric weather forecast. Then we have a consistency, full consistency, and we also, interpolate for all GNSS station, the static station, the numeric weather model parameters, including the auxiliary parameters for vertical scaling, and also we synchronize the data in by intertemporal interpolations. And then finally, we scale into the reference surface, which is selected to be mean sea level, because we do it consistently, so we don't care too much if it is orography or it is a reference level. It's following really the paper which is in the GRL, and in fact it uses lapse rates and the decay parameters for the different parameters individually, well calculated through the background model from the numeric weather forecast. And then we do the special interpolation for using the simple kriging and variogram estimated within the kriging, and so to estimate what is in the location of the zenith GNSS stations to get the information in the numeric weather model grid. So in the same resolution as the numeric weather model grid. And finally, to interpolate again in vertically or scale it into the numeric weather orography, because our model is driven by the numeric weather orography. Again, using the same procedures as in down scaling to the reference level. And optionally, if we have now two resources of the zenith weather delay from the original from the numeric weather model, so our first layer model, and then additionally from the GNSS, we can do a play around with the combination of these, and this will be study cases which I will show you later on. How to assess it? We assess it optimally by the GNSS. And initially, we just use all points as a control points, which means we could validate our original first layer of the numeric weather model-based corrections only. Then we can have a closed loop scenario where we used all the input points from the GNSS as a control point as well. So that's can really assess the impact of our interpolation methods and strategy, etc. And finally, we have done a reduction of the input points and two different reductions. So every third input point was control point only, or every second input point was control point. And this was really the assessment which we have done finally. So here are the differences at the GNSS locations at the network. And this is our differences between the zenith total delay. So it's an assessment or the comparison of the numeric weather model based correction and the GNSS, what is sensed in the GNSS. And you see it's still it's a quality of the numeric weather model. For the WRF model, it's about 1 centimeters in standard deviation. There are also some bias. These are just snapshots for two epochs. And this is era interim, where you see that the low resolution model can really has some problems with some stations, of course, because resolution is 100 kilometers. And then if we interpolate it spatially into the numeric weather model grids, and now only WRF in 4 epochs in 1 day, 6 hours time resolution, just to make samples, you can see the differences between already two components on the zenith weather delay, which we are aiming to combine, in fact, optimally. And one is from the numeric weather model poorly, and one is from GNSS by subtracting zenith hydrostatic delay and using the procedure. And this is exactly, you see already, it's still 5 centimeters in changing the differences there. And in fact, this is something which is an inaccuracy of majority inaccuracy of the wet component in the model. So that is our potential improvements by using the zenith weather delay. I showed you a snapshot of the one epoch or several epochs, and here it is over the, let's say, daily statistics over 50 days of the benchmark campaign. And you see for the era interim low resolution model, and for WRF a high resolution model, and for the forecast operational model, you see that the standard deviation is what I showed you is about 1 centimeter in let's say overall for all stations and over all time, but nevertheless is highly variable, and also you can see a quite high biases there in the model, which is quite typical also. And now, after applying our combination and after substituting the zenith delay instead of the numerical model zenith delay, so just playing around, not combining but replacing the values for zenith delay and controlling the closed loop, we can see how it can really improve the performance of the modeling. So again, in error interim, we still see some bias, but in a high resolution WRF, so this is an error of our procedure, in fact, because this is a closed loop scenario. And then we can still play around about the combination of these two zenith delays. So we set up different scenarios. One is, let's say, to dominate with a GNSS. This is the replacement, in fact. So not use any NWM zenith delay anymore. Then by a factor of 2 better, let's say, accuracy for the zenith GNSS zenith delay by using the Kriging statistics or accuracy, or equal 1. And this is in fact the background scenario where we use the zenith delay original from the numerical model. And these scenarios we assessed. And coming into the table, you can see that in fact we dominantly in any different scenarios of the reduction of the grid point, so to use some input points as a control point. This is exactly this scenario when half of the points were used only as an input and another half of the point of the network, GNSS network, was used for the control. And you see that the scenario where we simply replace zenith delay in this nice scenario where we have a nice dense network of GNSS over all area, then it's a best scenario that we really trust the GNSS there. And we evaluate it in the way that this is a closed loop scenario, so this is the accuracy of the strategy for the error interim and for the high resolution model, so no almost bias. And this is really independent assessment where we get improvement about 40 to 50% above the original scenario. And now looking into we have still, we could notice here that we have a different resolution plays really a role here. So you can see it in this number that the closed loop scenario works much worse in this low resolution model. So we thought about if we use an error interim low resolution model and artificially increase the resolution, then what is the impact? And we can see it here again, A, B, C, D. So from this part, it's just a replacement of the zenith delay from the GNSS, and this is equal zenith delay from GNSS and numerical model, and these are in between scenario. And you can see the impact is really dominating when you have replacing zenith delay and you are artificially increasing the resolution of the numerical model. Simply, you are getting much more information from GNSS and really taking a benefit of this. And very interesting here is that we could get rid even mainly of the bias of the model, this low resolution model. So the resolution was behind the keeping there the bias. And here is again the statistics over all time and the different, let's say, increasing the densification of the numerical model. So this is the original scenario. And then finally here it was, let's say, reduction from 100 kilometers up to 12 kilometers, something like this. And you see that it works very well even so that we could really reproduce what we expect from the GNSS ZTDs when we used this independent assessment of the half of the point as an input and another half as a control points. And finally, we have another scenario because practically we will use the operational high resolution model. And in fact, the resolution model has a 9 to 9 kilometers, so it's very high resolution in terms if we have a GNSS 50, 70 kilometers in the standard reference network. But we can estimate in real time or near real time gradients for the zenith total delays. And we can again subtract them and try to calculate the pseudo gradient, so that's pseudo ZTD. So that means we can take information from the gradients on the local of the GNSS and to try to double the number of input from the GNSS into this combination. So by this, so we calculated the pseudo ZTDs for each station in the distance of 15 kilometers in the direction of the minimum gradients. Here is a snapshot how it works. In fact, there are two cases, 15 kilometers and 25 kilometers far, these pseudo ZTDs, and these were again input as an input point and control point for the assessment. And you see again it was applied only for the high resolution model, WRF operational one. So this is the original scenario using all ZTDs and pseudo ZTDs for the verification, and this is what we get after the replacing of the GNSS information. And here again the statistics, and mainly we focus on, let's say, this original zenith total delay and using the pseudo ZTDs. So that original scenario really looks that we had. So this is the assessment of our strategy. So this is something which we are targeting and which is our limitation because we do interpolation in between, etc. So we cannot get something more better than this one. So all points are control and input. But here we have a 50% of the point as an input and 50% of the control, and we see that we are almost there. So we are not losing really the accuracy due to this interpolation scheme, etc. And we can take a real benefit of the zenith total delay from the GNSS as well as the gradients in this particular case. And so this pseudo ZTDs still improved about 35% the standard deviation. And my conclusion is, so we have developed this dual layer concept where we have a background layer, which is really one which is a trustable one because it's a weather forecast, the same resolution over the whole area. And in fact, only this is an optional layer, but which can take a really benefit of the reference network in a local area. For example, national reference network. And then by using the simply replacement of the zenith delay, so the humidity component from this GNSS, by a procedure which is a really sophisticated and well done, all these interpolations and in temporal and spatial domain and vertical scaling mainly, then we can get improvements about the 40% over the original model. So that's an advantage of this additional layer. And then this impact study shows that even we can, it's very important to have a high resolution to take a benefit of this high resolution GNSS. So that's mean for era interim, it was well demonstrated, but then it's very interesting that even gradients can contribute from GNSS into this combination. So that means creating the pseudo ZTDs, which are still valuable information about the zenith total delays. And this is, from our point of view, a super method for the tropospheric augmentation service if we have these two informations and to do it well. And it can be applicable on the surface and above the surface as well. Thank you for your attention.